wave number recovery by 2D frequency domain full waveform inversion from slowness and source frequency limited elastic seismic data. This work is carried out on 56-core Intel Xeon X5650 cluster at UT Dallas. My research heavily relies on parallel processing, memory bandwidth, math kernel library, and multi-node scalability. Beyond computation, visualization and signal processing tools such as MATLAB, Canvas, or low-pass filters, and Python libraries are used for analyzing and interpreting my research results. Here is the outline of my presentation. I'll start with a brief objective of my presentation, followed by numerical solutions, main ideas, elastic FWI examples, spectral amplitudes, model impedances, and then conclude with the summary and conclusion. The objective of my problem is to quantify the relationship between wave numbers in an illuminating wave field and the wave fields that are reconstructible in the target by migration or inversion. The approach to the problem is by using the definition of wave number, which is k equals omega p. To illustrate the contributions to k from the frequency and omega and the distribution of the source receivers contained in the slowness p. The application is optimization of data acquisition for specific target survey geometries and frequencies, to invert for distributions of elastic properties, to generalize the solutions for arbitrary geometries, and to allow quantitative analysis. It's useful to do numerical, which is frequency domain or finite difference simulations, to calculate the differences between the reconstructed and correct models, or the corresponding 2D or 3D Fourier spectra, or the image correlations of 1 and 2. The main ideas are the full waveform inversion can be done in a multi-illumination pattern with different apertures. A few frequency components are enough to perform modeling and inversion. The inverted model updates contain higher wave numbers associated with parameter contrasts. The background models contain the low wave number portion of the parameter distributions. So ideally, these two together provide a continuous distribution of wave numbers whose spectra can be compared with the spectra of the known target models. The elastic full waveform inversion algorithm inverts for three elastic parameters: p velocity, s velocity, and density, simultaneously in the frequency domain for the velocity model using time domain full wavefield short gathers. It uses two strategies to mitigate the nonlinearity: an improved time domain finite element method, finite element modeling method used for elastic wave field simulations, while the inversion is implemented in the frequency domain via discrete Fourier transform, enabling frequency selection and time windowing to reduce nonlinearity. And progressively increasing frequencies and also like parameter decoupling is achieved via a multi-step-length gradient approach that searches for optimal step lengths in a combined gradient correction or iterations. And progressively increasing frequencies are added as iterations proceed to avoid cycle skipping. Elastic full waveform inversion test on the finite difference synthetic data for the Marmouzy 2 model. So in my simulation, I'll be using two sets of velocity and the density models. One is true and the other one is the starting velocity model. The true velocity and density models are the models from which the synthetic seismograms were computed. The starting velocity and density models are the input model of the elastic full waveform inversion. Both are discretized into 920 by 304 with grid intervals 0.01 kilometer. With uniform interval of 0.01 kilometer, to remove unwanted model edge reflections and free surface effects, a hybrid observing boundary condition is put around the four edges of the models. The VS model is generated from the true BP model using the ratio PP and VS, and the density is generated from the P velocity using the Gardner's relation. The survey aperture considered contains there are two different approaches. In one approach, the sources and the recorders for the geophones are used all along the surface of the model. And the number of the shot numbers are 111 shots on the surface, and the receivers of the geophones are 231 recorders along the surface. And in the second survey aperture, that contains total number of shot numbers are here, 111 on the surface, and there will be some more shots along the edges of the grid, which is 33 along both the left and right sides. So total is about 107 shots are used for this kind of survey geometry. And the receiver numbers are 231 on the surface and 73 along the sides, a total of 377. And each of them are about 0.04 kilometer spacing and 0.02 kilometer spacing. And we apply the frequency selection strategy in two phases, group 1 and group 2. And in group 1, we apply 15 frequencies with equal interval of 0.3 to 6 Hz, starting from 3.09. If we keep increasing with an interval of 0.3 to 6, and 15 frequencies will be, the 15th will be 7.65 Hz. Similarly, for the group 2, there are 15 higher frequencies with same interval, starting from 7.97 Hz to 12.21 Hz. In phase 1, a set of lower frequencies with an equal interval of 0.3 to 6 Hz are used for 30 iterations for the inversion. And in phase 2, a set of higher frequencies, as shown here, are used for another 30 iterations or until the model converges. They are divided into two ranges, and the resulting elastic model, which is used as the starting model to fit the higher frequencies. The frequency increment is small enough to prevent frequency leakage. And here the figure I show this is the true Marmosy 2 model, and this is the starting Marmosy 2 model. And as you see, the Marmosy model consists of three different figures. The top one is the P velocity. That is, the velocity range is between 1.5 kilometer to 4.5 kilometer, as the color bar indicates the velocity at different with the different color ranges inside the model. And the middle one is the VS velocity, VS Marmosy 2 model, and the bottom one is the density model. And the color bar, the VP range is 1.5 to 4.5, and VS is 1.0 to 2.5. Density goes from 1.8 to 2.6. So the reason behind selecting Marmosy 2 model is because of the relation K equals omega P. To recover a complete model wave number spectrum by full wave inversion requires that the illuminating source wave fields contain combinations of wavefront slowness and source frequencies that correspond to all the wave numbers in the model. And examples using elastic data for a model with Marmosy 2 model illustrate these relations. So in this model example, the impact in model fitting is much larger for increasing the acquisition aperture. As you can see, the velocity variation is different at different layers of the model. So it is much larger for increasing the acquisition aperture than for increasing the frequency bandwidth because of the range of diffs in the Marmosy structure. And the starting model, which is created from the true model, by smoothing the true model using a 2D Gaussian filter with a correlation length of 1.6 kilometer. And the smooth model is the input model to the inversion. And the impedance model is created from by multiplying velocity with the density. So the P velocity and density, when we multiply, we get the IP impedance, the P impedance, and when you multiply VS with density, we get the S impedance, which is denoted by IS and with the color bar. This figure shows the two-component vertical and horizontal component elastic particle displacement whole wave fields for the 101th shot. The shot gathers are simulated in the time domain using a recurve wavelet with a peak frequency of 6 Hz. The recurve wavelet is shown in color red with time sampling increment of 1.5 millisecond for each expressive shot recorded with 4,096 time samples. And this figure shows the true Marmosy model and the inversion results of the Marmosy model using the two different survey geometries. And the left column contains two Marmosy model A. The top one is for VP, the middle one is for VS, and the bottom one is for the density. And the middle two columns, they are the inversion results of the true model using the sources and recorders only along the surface. And these two columns are the inversion model of the true model using the source and recorders along the three edges. And the inverted images are after 60 iterations for these two, and this is also after 60 iterations using the complete frequency bandwidth. This is the first phase frequency bandwidth, the inversion results. This is the second phase frequency bandwidth. So the second phase frequency bandwidth contains all the 15 plus 50, 30 frequency ranges. Similarly over here. And this figure shows the image correlation plots between the true and the inverted model velocities and density. And this is the figure for the P, VP, PS, and density, the IC plots of the VP, PS, and density for the source and recorders on the surface. And this is the same IC plots for 3 parameters using the survey geometry for the along the 3 edges. And the correlation coefficient is calculated using this formula. And as you can see, when the sources and recorders are along the surface, the correlation coefficient calculated value is 0.7722 for the velocity, and for along 2 edges and along the surface and along all the edges is 0.78104. And the gray and the this one is the red line is the theoretical location of perfectly recovered elastic parameters, which has to be 1. And the gray scale indicates the relative data density, which is the points per unit area. This figure shows the Fourier spectral amplitudes as a function of wave numbers of the images. In column A contains spectra of the true model. This contains the spectra of two models for VP, PS, and density. And this contains the spectra of the inverted models from the data of the source and recorders or the geophones on the surface. And here it contains the spectra of the inverted model from the data of the source and recorders along the surface and the 2 edges of the Marmosy model. The upper row is VP, the middle row is VS, and the bottom row is density. The Wavenumber spectra of the true model parameters are complete up to the Nyquist sampling of the Wavenumber in the models. These spectra are defined independently of any subsequent partial illumination produced by complete omega or P data. So the reduction in the bandwidth of K in FWI, that is full-waveform inversion, can be thought of as a filtering of the complete spectra by omega and P limited operators associated with the limited omega bandwidth of the source, or the limited P aperture of the data acquisition. As it could be clearly seen, the Wavenumber spectral amplitudes are recovered higher when the aperture geometry is higher. So in this figure, I'm showing the spatial distributions in improvement in the inversion. So this figure shows the spatial distributions of the improvement in the inversion results obtained by increasing the frequency window from 3.09 to 7.654, which is about 15 set of frequencies, to 3.09 to 12.218, which is another 15 set of frequencies. Altogether is 30 set of frequencies. This is the inversion results in the first phase. And this is the inversion result from 3.09 to 12 using all 30 set of frequencies. This is the survey geometry, and this is for the other set of survey geometries. As could be seen, the inversion results are better when the survey geometries are along the 3 edges. So this right figure shows the spatial distributions of improvement in the inversion results obtained by increasing the acquisition aperture. So what we did here, the source and recorders are along the 3 edges, And this is only for the low frequency window, that is from the first phase 3.09 to 7.654, and this is for the next set of 15 frequencies, which is altogether 30 set of frequencies. So as we can see, for only along the, when the source and recorders are along 3 edges, this is how the recovery is higher for the full frequency window. Here is the spatial distribution of Wavenumber recovery as functions of spatial aperture and frequency. So here were the sources and recorders in the surface only, the difference between column 3 and 1. So this is the earlier slide what I showed. This is the true model, and this is the inverted image using the set of frequencies for the sources and recorders only along the surface. And this is the recovered, the impedance results, the image recovered images using this full set of frequency range, and now using the second set of geometry, which is along the 3 edges. And these are calculated. These are the calculated. This is the difference between column 3 and 1. So that's the result which is shown here, which is not recovered by the inversion. And similarly over here, it is the difference between column 5 and 1, and which is not, which is, these inversion results are not recovered. Similarly, for the spatial distribution of improvements in the inversion results obtained by increasing the frequency window from first 15 set to the next 15 set, and here using the sources and recorders only on the surface, here is the difference between 2 and 3, and the result is shown here. And here is the results along the edges, source and recorders along the edges, the difference between column 4 and 5. And as you can see, the image improvement values are larger in B. And the maximum speeds for BP, VS, and rho are approximately 1.7 km per second, 0.9 km per second, and 1.2 per gram cubic centimeter. So here we are showing the spatial distribution of the improvement in the inversion results obtained by increasing the acquisition aperture. And here we are using only the low frequency window, the difference between the columns 2 and 4. And using the full frequency window, difference between the column 3 and 5. So that difference is shown here. And here I'm showing the model impedance. The model impedances are calculated by multiplying the velocity with the density. So in the top, I'm showing the true velocity, true model impedances, and the bottom, I'm showing the inverted model impedances for the three. This is for the true model. This is for the sources and recorders only along the surface, and here is the sources and recorders along the 3 edges. And in the right side, I am showing the cross plots between the original IP value, original impedance, there's the P value, which is shown in the top row, and the recovered IP value. And this is the ideal, which is the, and this is the original IP value and original IS value for the source and recorders along the surface and the 2 edges. And similarly, this is for the source and recorders on the surface for IP and IS, and this is for the sources and recorders along the surface and the 2 edges for both IP as well as IS. And the IS images have higher resolution than the IP images from the data, as could be seen from here. Frequency bandwidth, because the range of this S wave numbers is higher than that of the P wave numbers. So the cross plots between the original and the recovered IP and IS wave amplitudes for both source and recorder orientations, and for the source and recorder orientation along the 3 edges can be seen higher compared to this one. And these results are much more higher compared to the results that we got. The impedance correlation coefficient values are much more higher compared to the only velocity and density values, which is about 0.7 and this is about 0.9 range. And the grayscale gives the data density, the number of data points with a sampling box centered at that location. P and S impedances are fitted better than the velocities and densities are separately. And the red line corresponds to the R-square values when the true and predicted values are equal, and which is ideal, that is equal to 1. And the R-square values for the velocities and densities are all less than 0.78, as we see in one of our earlier graph. And in this case, they are about 0.91 for both IP and IS. So the wide aperture configuration produces larger R-square values because the model is sampled more completely. The summary is, in comparing the reconstructed models with the true model, the corresponding IC plots, the R-square values are consistently slightly higher when the sources and recorders along 3 edges are used. Expanding the source and recorder apertures to include the 2 vertical edges increases the Wavenumber bandwidth in the inversion by improving the recovery of the dipping features in the model, but is still not as complete as that of the true model. So the Mormosy 2 model example, the impact in model fitting is much larger for increasing the acquisition aperture than for increasing the frequency bandwidth, as we saw in one of the slides. The recovered Wavenumber bandwidth of an inverted model will always be smaller than that of the correct model because of the frequency of the source wavelet is band limited. And any real recording aperture parameterized by the slowness p is finite, as the relation between them is k equals omega p. And the computation of all the iterations is carried out at, as I said earlier, 56 CPU cores of Intel Xeon X5650 cluster in Dallas, and it took us about 110 hours. And this pilot study sets of stage for future evaluation of acquisition design, for optimization of inversion, to recover Wavenumber information from targets for various Wavenumber characteristics. So various combinations of sources and recorders, space or time, or the equivalent Wavenumber or frequency representations of it output is recorded. Its recorded data and its spectra can be simulated prior to field data acquisition to maximize the information recovery and to quantify the corresponding cost or benefit trade-offs. The impedances from the products of the velocities and density compensate for their under and overestimations of the deviations. So my work leverages Intel Xeon processors. I have been able to execute large-scale parallel simulations efficiently, and I plan to continue exploring Intel's newer architectures to further optimize the performance of large-scale seismic simulations. With this, I come to the conclusion of my presentation. Thank you for your time.
Great, thank you. Very interesting. So we have time for a few questions. Let's see if there are any in the chat.
I have a question. So did you run it on, like, how many nodes did you run these experiments?
We ran on 16 nodes.
Okay, and do you have any scaling numbers for those? Like, how do you see the performance increasing the number of nodes or processes or all that?
Yeah, I don't have a figure not right now. Yes, maybe I'll try to get it. I mean, if I have, we'll try to find it next time.
Good.
And do you think it'd be, I know on the Aurora system, the CPUs have 64 gigabytes of HBM. I don't know if you had thoughts about using high bandwidth memory that is closer to the CPU, if you think that would speed things up.
Okay.
Do you know if you're more compute limited or memory bandwidth limited?
No, it's more compute limited.
Okay. Yeah, so that might not help a whole lot then.
Mm-hmm.
Well, good. I think that's all the questions we have. Sasmita, thanks so much for putting the presentation together and joining us.